Hello, my name is Alexa Reed. I'm a senior in Biological Systems Engineering at Virginia Tech. My advisor for this project is Dr. Hession, and today I'm going to be talking about my spatial analysis that I did for salinity in Stroubles Creek. So to give you some background, the reason for this study is that salinization is a threat to freshwater ecosystems. There are many sources of anthropogenic salt pollution, such as sewage leaks and discharges, water softeners, and agricultural fertilizers. The source I will be looking at for this research is road brining, which you can see here on the bottom right. This project expanded on research done by a group of Interface of Global Change Fellows. They used 8 years of data from one site at Streamlab. They concluded that it is a complex issue and that there was a need for more spatial analysis to account for land use and other variables. So the Virginia Tech Global Change Center provided a grant for additional sensors, which gave me the opportunity to conduct this research. In order to get the data for this project, I installed an extra 4 sites along Stroubles Creek. Sites 3 and 4 are Bridge 1 and 2 at Streamlab, and then I installed sites 1, 2, 5, and 6. You can also see that sites 1 through 5 are in a mostly urban landscape with some more agricultural influences around 2 through 5, and then the last site is in a more forested landscape. Pictured are 2 example sites, and then this is the basic timeline of my research. I installed the rebar and deployed the sensors on July 24th of last year. Included on this timeline are the brining dates, which are the focus of this research. I was also collecting data about once a month and going out periodically to check on some of the sites. To start with the data analysis, I plotted specific conductivity in microsiemens per centimeter and stage in meters, which is the water level. These are all from the same storm event on December 16th, which occurred after they brined the roads on December 15th, shown by the red star. You can see that when there's a hydrologic peak in the stage, there's also a spike in conductivity. As you go downstream, the conductivity concentration decreases with the exception of Bridge 1, which peaks at 1200 since it is downstream from the Fox Ridge culvert. The last site is around 550 microsiemens per centimeter, which is the farthest downstream and is surrounded by forest, which you can see is an important factor. Another concept seen here is the delay in the hydrologic peak in stage as you go downstream. You can see it best in the last site where the delay is more distinct, and as you can see, the peak in the red line is much farther right. After that initial analysis, I looked at hysteresis, which is the temporal lag between increases and decreases in discharge and the concentration of a solute. To graph hysteresis for this analysis, I plotted stage on the x-axis and conductivity on the y-axis. On the left, you can see them separately for the storm event, and then on the right are the hysteresis graphs. A counterclockwise behavior is seen as denoted by the arrow indicating a dilution effect, since the conductivity doesn't start increasing until the stage peaks and then decreases. The next set of graphs shows an example of clockwise hysteresis, which is flushing or first flush effect. And here you can see the conductivity increases before the stage does, and then once the stage hits its peak, the conductivity is already back to normal levels. As you can see, half the sites were counterclockwise or diluting, and half were clockwise or flushing. Sites 3 and 4 showed signs of figure-8 loop behavior, which indicates that there are multiple peaks of the variables, which could explain why there's a discrepancy at Bridge 2 with a counterclockwise effect rather than clockwise. Since a clockwise loop is seen when the concentration increases quickly compared to the stage, which suggests a close source of solute. This clockwise loop behavior is seen at sites 2, 3, and 5, which makes sense since they are in a more urban landscape close to the salt source. Site 1 is also in an urban landscape, however, since it's below the duck pond, that could be influencing the conductivity levels at this site, since the pond could be storing salts and slowing transport, making it more complex. Then at the last site, we see a counterclockwise loop, which shows that conductivity concentration increases slowly compared to the discharge, indicating a distant source of solute, which makes sense for this site since it is surrounded by a forested landscape which can act as a buffer from the urban landscape and roads. So the conclusions gained from this research is that freshwater salinity in Stroubles Creek is extremely complex, as you can see from the differences in the hysteresis plots in these sites. Additional sensors did improve the spatial knowledge, but also reinforce the complexity. Distance from brined areas and distinct stormwater outfalls drive changes in salinity, like at Bridge 1 next to Fox Ridge. The ponds are likely an influence on salt movement, since the first site, which is below the duck pond, is seeing discrepancies that I talked about. And then for the future, adding additional sensors above and below the ponds could be beneficial to explain these more complex issues. Brining data from the town of Blacksburg is needed since we only had that information from Virginia Tech, and there will be continued monitoring of these sites for temporal data. I would like to thank the following groups and people for their help and funding, and thank you all for watching.